Okay, so we just looked at unitary transformations on states. So now we're going to look at unitary transformations on operators. And so, in fact, let's just start again. We're going to kind of keep this same generic operator, A hat, and let's just have its eigenstates denoted in this following way. Psi sub n, right? A hat upon psi sub n is equal to lowercase a sub n, psi sub n. Okay. And so what we're going to do is we're going to define the unitary transformation of a hat. And so in this example, a hat is an operator for an observable. So it's Hermitian, right? And then what we want to do is we'll define the unitary transformation of a hat. So we'll call that a hat prime, and that's going to be equal to our unitary operator u hat acting on a hat, acting on u hat dagger. Okay, so we'll sandwich our operator that we're transforming between u hat and u hat dagger. Okay, and so now the first thing that we want to show is that expectation values are preserved. This will be, so we want to show that expectation values are preserved between a, so we'll have psi in a hat, psi n versus psi n prime, a hat prime, psi n prime. And I just want to point out really quickly that for the example of expectation values, maybe I shouldn't have picked eigenstates of a hat. That's not quite necessary. I do want to show you, though, that the eigenvalues are also preserved. So that's why I wanted to use the eigenstates of a hat. But anyway, let's just go ahead and quickly show you that this doesn't change the expectation values. And that result won't really depend on if we're using the eigenstates of the original operator or not. But right now, we are using the eigenstates of the original operator. Okay, so now recall, right, we have psi n prime is equal, on the bra, is equal to psi n on the bra with mu dagger. And then we have psi n prime on the ket is equal to u hat on psi n, right? And so then if I'm going to actually take this expectation value on the right, where I have psi n prime on the bra, a hat prime on the ket, sorry, a hat prime in the operator, and psi n prime on the ket. And what I'm going to do is I'm going to expand each one of these. So the bra, I'm going to expand as psi n on the bra with u hat dagger. And then a hat, right, I'm going to expand as u hat, a hat, u hat dagger. And then psi n prime, I'm going to expand as u hat, psi n on the ket. Okay. So now what I can see is I've got u hat dagger times a u hat here, and a u hat dagger times a u hat here, each one of these is going to give me an identity. And so overall, this is just going to give me psi n a hat psi n. All right. And that was the original expectation value with my original state psi n and the original operator a hat. So if I take the expectation value of my transform operator using the transform states, I will get the same expectation values as I got with the original states and the original operator. So now, finally, let's take a look at just simply taking a hat prime and acting on psi n prime. Okay. So now remember that I can expand a hat prime as u hat, a hat, u hat dagger, and then I can expand psi n prime as u hat, psi n prime, psi n. Okay, and now I see I have here a u dagger u, which is the identity. And so overall, this gives me u hat first, and then a hat on psi n. So now this is the original operator a hat acting on its original eigenstate psi n. So this is the same thing as u hat multiplied by a sub n and then ket psi sub n. Okay, so I've got a number here, I've got an operator here, and I've got my ket here. Okay, so now the number I can just move over, right? And finally, what I can write this as, I'm going to just draw an arrow down here. So this is the same thing as a sub n, the original eigenvalue, multiplied by u hat on psi sub n prime, so psi sub n, which is equivalent to saying a sub n acting on psi sub n prime. Okay. So what does this tell you, right? So the transformed operator has the same eigenvalues as the original operator. Now, does it have the same eigenstates as the original operator? Eigenstates, it does not, right? Its eigenstates are related to the eigenstates of the original operator by the unitary transformation. Which, and of course, there are many unitary transformations. So specifically, I mean, it's the eigenstates of the transformed operator are related to the original eigenstates by the same unitary transformation as you used to generate the transformed operator, right? So this u hat that I'm using to get psi n prime, it's the same u hat that I'm using to get a hat prime. Okay, so there's some really nice relationships between that that these unitary operators have. And so one of the things that you can see is that if I'm going to do something like take the unitary transformation of a Hamiltonian, then what I expect is that the new Hamiltonian that I get out, right, the transformed Hamiltonian, is going to have the same eigenvalues. Okay, so that's really important. So we're going to be taking our Hamiltonian P dot A, right, and we're going to generate a new Hamiltonian by doing a unitary transformation on it. So we'll take U and U dagger, right? And this is going to give us a different Hamiltonian, which we're going to call H D dot E. And, and then similarly, we'll take a different set of transformations, and that's going to give us, so I'll just draw other set of unitary operators like this, and that's going to give us H polypherts. And so basically what I can say, because all of these Hamiltonians are related by unitary transformations, they all have identical eigenvalues. And states, eigenvectors or eigenfunctions, whatever, are related by unitary transformations. I'll just call them unitary rotations. Since I use the word vector, then I think unitary rotation is a nice language to use for it. Okay, so that's great. So that means that the ground state energy of P dot A has to be the same as the ground state energy of polypherts and of D dot E, and the first excited state energy of P dot A has to be the same as that of D dot E and polypherts and so on. Okay, now one of the things that you may sort of wonder after I made that statement is like, okay, well, if they have the same eigenvalues, then what is the purpose of the transformation? Because it seems like I should get the same results either way. So if I started out by writing P dot A, why not stop there? Why bother with this transformation? So yeah, the operators have identical eigenvalues, but remember, when we are actually doing practical computations, what we're going to do is we are going to build a matrix of these Hamiltonians in some basis. And as our basis approaches completeness, the numerical eigenvalues of that matrix will approach the true eigenvalues of our operators. They don't exactly match, right? And outside of this complete basis set limit. So the real advantage goes back to what I was saying earlier in video 1 about a good basis for the polypherts Hamiltonian in D dot E compared to a good basis for P dot A, right? If I have a good basis for computation, basically it means I don't need some gigantic number of basis functions to start to get closer to the exact eigenvalues. On the other hand, if I have a bad basis, I typically do need a really large number of functions to start approaching the numerically exact eigenvalues. So basically what we get by doing this transformation is we get to sort of see good numerical accuracy for the eigenvalues of our matrix representation with a relatively small basis. That's what we get. And that makes a really big difference when you're doing computations. Okay, so that is the last thing I want to say about some of these nice properties of unitary transformations. And what I want to do in the final video is actually apply this transformation to the P dot A Hamiltonian and show you how to work through that. And then we'll come up with a practical or an actual expression for the D dot E Hamiltonian, which we could implement on a computer, just like we did for the P dot A.